We are the time clock switched receptacle group. We request that questions are held until the end of the presentation. When we first developed our problem definition, we were too focused on including every aspect of our project, rather than identifying how our project created value. As such, we removed references to our client, how our product would function, and specifics on how installation costs will decline. We identified that value will come not just from override capabilities, but from intuitive controls, and that we do not want any additional controlling devices outside of the master receptacles. Furthermore, we more clearly identified the certifications that are relevant to providing value. In the end, we based our problem definition on the value our product creates in providing scheduled power delivery to office buildings, providing intuitive manual and web-based controls, allowing for comparable power savings to products currently on the market, and having a lower production and installation cost. We also now know that LEED certifications and many municipalities are requiring switched receptacles for office buildings, so having our device comply with these standards is vital.
Our initial stakeholder feature model did a pretty good job of demonstrating which specifications should be the most important to our project. Many of these specifications will contribute to our device following many LEED and municipality standards. We modified the model on the right to include weighted boxes on the feature side to show which features ended up being the most important. As well, we added a few new features that were brought up by either our client or potential users. Some of these features are that the receptacle must be a standalone device, that they need to be easily identified, and that we would use a web app for control, rather than a central control unit. Finally, we removed the feature of being easy to reprogram because we are no longer making the device reprogrammable. On top of these feature changes, some of the line thicknesses changed to indicate a change in importance. Our initial mind map was constructed to focus on the very early objectives of our project, creating a functional switched receptacle. Our 4 sections of the mind map, system, form, performance, and function, were filled out using research and interviews. As we built out the branches, it helped us identify what would need further exploration so that we could figure out what would lead to a successful project. Throughout the process of continuing research, the mind map expanded significantly. Choices that seemed more likely to be used were highlighted in green, while those that were unfeasible or difficult were highlighted in red. Our current mind map shows a lot of the technologies that we have explored further, which helped greatly in our initial prototypes. Still, there is more research to be done in all of these areas, especially in the event that the team needs to pivot to one of the other choices on the mind map.
Since the first time we presented it, our impact table is only slightly changed, and these additions can be seen outlined here in purple. The most important of these changes has to do with the new hard constraint offered by our client, which is that the receptacle must not rely on any additional external hardware. Essentially, a user should be able to purchase the receptacle and not need any additional products or installation in order to make it run. The other addition at the bottom of the table is in response to an increased attention to safety concerns, specifically overheating. This impact will be addressed by including a factor of safety on all rated components and through extensive failure testing. The rest of our impact table has remained relatively the same, only receiving a few minor tweaks. Several of the impacts that we had selected have been reinforced through interviews, such as confirming that our product will make for significant savings on installation, as well as the necessity of the product being UL listed if it is ever to see widespread use. Through research and calculations of our own, we have also confirmed that users of our product will indeed see a significant reduction in wasted energy, despite the power required by the receptacle's microcontroller.
The major takeaways from our user interviews were firstly allowing us to identify how our product would create value. From there, we spoke with our client, facilities, office workers, and building managers to identify the office building as our main marketplace. We faced a significant hurdle when we discovered a patent for our product, as well as a similar product currently on the market. Interviews with our client and professors allowed us to use this revelation as a growth point for making a more desirable product. From there, we identified Wi-Fi as our main method of communication and Tri-X as our switching component, through discussions with professors and professionals. Finally, it was through interviews with professors that we identified challenges we need to overcome in using a robust antenna and designing sturdy and appealing device housing.
Shown here is an abridged version of our current list of system-level metrics and tests. We initially included resilience and heat generation, and then later added ease of use, bandwidth, and power usage based on various feedback expressing concerns for those portions of our device's function. These additions made a lot of sense and served to further fortify our plans for analyzing the success of our prototypes. Since this device will operate in commercial settings that almost always rely heavily on the internet, we must be sure that when scaled, our devices will not severely impact the overall performance of a building's network. Thus, we need to measure the amount of data that our device sends and receives during different stages of its operation. Ease of use is especially important to users and potential buyers of the device, which is why we decided to include it. This metric is more on the qualitative side, but will still be extremely useful in helping us gauge the user experience of our device. Finally, the power usage was added because even though a more power-consuming device would still achieve the goal of meeting certain building codes, the added benefit of net power savings will serve to make our product more appealing to potential users. Initially, our Level 0 use case diagram had a very broad scope and involved several different parties interacting with our device in a wide variety of ways. However, over time, we decided that we needed to focus more on the actual functions of the device and the ways in which users would interact with it. Thus, we removed use cases such as production, design, and sales. This allowed us to get a much clearer picture of what actions our device would actually need to perform. For our initial Level 1 use case diagram, we tried to keep things simple, but ended up oversimplifying some of the components to the point where the diagram was not as useful as it could have been. We also felt that it did a poor job of thoroughly explaining which actions each of the three main blocks performed and how those blocks interact with each other. Our most recent Level 1 use case diagram clearly delineates the three main blocks of the device and shows how those blocks will interact. We updated the labels on the lines connecting blocks to reflect our decisions about various inputs and outputs. This use case diagram reflects the important functions of each block, and thus is much more useful. Our main iterations regarding the Level 0 block diagram involved the method of entering in timing information and configuring the device. Initially, we weren't sure of how a user would input scheduling information to the device. After some research, we decided that the most effective way to achieve this would be to have the data input through a web portal. This change is reflected in the diagram on the right. As we got more specific about how our device would function, we were able to start sketching up a Level 1 block diagram. On the left is the first one that we sketched when we were initially trying to visualize our device. As we moved through the design process and hammered out more details, we were able to add a lot more information and complete the diagram, including all of the necessary inputs and outputs. The chart on the right reflects these changes, yet does not show the boundaries of each block as much as we would have liked. The most recent Level 1 block diagram is shown here. This shows the entire system divided into the three blocks, as well as conveys which components will be physically inside the device and which will be hosted on the server. These changes convey much more useful information and will be extremely helpful in coordinating integration.
Power control subsystem consists of two distinct parts. The AC to DC converter will provide 3.3 volt DC to MCU circuit. The track circuit will control AC power. The opto isolator will isolate DC from AC circuit, and the LED will indicate status of track or smart receptacle. Main challenges associated with power control include size of AC to DC converter, heat dissipation, housing, and integration of power control subsystem with the MCU circuit. Some applicable standards include NEC standards for number of receptacles, wire type or size, housing type or size, and others.
Early in the semester, we had considered override controls in the form of a physical wall mount, mobile app, or web app. The web app was chosen because in an office setting, all employees will likely have direct access to a computer. With this web portal, however, we are figuring out the solutions to two of our major challenges. In terms of communication with the MCU, we are still conducting research on exactly how we can get the two talking over a wireless network. IEEE standards 802.11 and 15 relate to bandwidth and communication, so while they don't relate to this issue, they will be helpful to deal with the scale of our device. Secondly, to identify each receptacle, we are thinking about allowing office managers to create a name system for their individual offices, and be able to store these naming conventions in the database.
Being that the microcontroller will typically be inactive, one major challenge is ensuring that the MCU will maintain the state of the relay while in a low-power sleep mode. Thankfully, we have since learned that the TI microcontroller that we selected, the Wi-Fi-enabled CC3220, includes tools to mitigate this. Another challenge that we came across was the initial setup of the MCU's Wi-Fi credentials, though we've since solved this issue through discovering TI's free mobile application that takes advantage of the microcontroller's access point mode feature, which allows mobile devices to connect directly to the MCU and send it network credentials. A challenge that we have yet to solve is sending data between the microcontroller and the web portal, which will be one of the first tasks we address in Milestone 7.
Our critical path model lays out the amount of hours of work for all of the tasks relevant to our project, including the programming the MCU, web development, relay and power supply development, PCB design, and housing creation, with many levels of iteration and integration. The critical path is focused around the web control and integration between the MCU and web, as we foresee allowing for scalable configuration, developing an intuitive user interface, and ensuring two-way communication for systems testing to be a time-intensive task, with Wesley performing the majority of the web development. The Gantt chart displays how we plan on achieving all of our efforts in the upcoming semester, scheduled around calendar dates. Orange blocks display the levels of integration, purple blocks are the entirety of a milestone, and black blocks are the dates of milestone presentations. All other colors display the levels of iteration for individual tasks. The longest milestones we believe will be the M8 and M9 milestones, as we believe initial integration and testing, and the following repetition of iteration and integration respectively, will be very time-intensive to develop a final product. Here we can observe milestone presentation dates in order to separate them from the additional tasks shown in the Gantt chart, and clearly acknowledge the time we are allotting ourselves for each milestone, which corresponds with the hours allotted in our critical path model, assuming every individual works anywhere from 10 to 15 hours of work a week. Here we have identified all of the major design aspects of the project that design engineers will be working on. While most tasks are consistent with previous milestones, we have clarified that T will be working on housing, and Christian will work on antenna and additional component implementation for PCB development. We have already identified the exact cost of some of the components, such as the power supply, triac, and development board, and have recorded the cost of purchasing the provided number of components. After speaking with Matt Lamparter about PCB development, we have developed very conservative estimates of producing 3 PCBs in-house and getting some printed to be roughly $75 and $200 respectively. Similarly, we have provided a conservative estimate of purchasing the connectors, faceplate, and plastic materials necessary to develop our own housing to be roughly $100. From these estimates, we are confident we will stay well under our budget of $1,000.
Over the course of fall semester, my contribution to our project includes carrying out preliminary power calculations for our device and either power loads of some non-essential devices. As a design engineer for power control subsystem, I have identified different ways to implement the subsystems and prepared purchase list of the components I need for the subsystem. I have also built a prototype triac circuit consisting an opto-isolator, a triac, and LED that I will develop next semester.
My first main accomplishment was researching triacs, SSRs, and mechanical relays. I provided the pros and cons for each product, and once we had identified triacs as the most viable solution, researched methods of developing safe triac circuits with opto-isolators. My next major accomplishment was the planning work performed as project manager. I produced our most recent problem statement and scope, based off our product's value creation. I then performed research and collaborated with my group members to develop a critical path model, Gantt chart, and budget that everyone could agree on. Finally, my last major accomplishment was developing regular communication with our client in order to relay new developments in our project design and ask pertinent questions. This led to a variety of clarifications on project requirements that allowed us to provide value by ensuring the only device we have to install is the receptacle, differentiating our product from others on the market.
Before roles were assigned, I took up the job of communicating with the client about the early stages of the project. On top of that, I continuously conducted research on a wide range of topics before assuming the role as the web portal design engineer. Since then, I've been focusing my research to the point where I have found the listed technologies to be the most suitable for the development of this block. For Milestone 5, I also made a simple prototype with a general layout of how we might expect the UI to look. This will help as we begin to move forward with the development and iterate from user testing.
My most major accomplishment so far has been researching TI's Wi-Fi Starter Pro mobile application used to send network credentials to our microcontroller during initial setup. Though the application will ideally function as is, there is a chance we may need to modify the source code in order to send the MCU credentials for the enterprise networks often seen in the office buildings where our product will be implemented. I've begun looking into the feasibility of doing so. I have also been largely responsible for creating the MCU's theoretical software architecture and will continue to develop and implement the software next semester. Additionally, I've served as the lead when looking into both the internal and external impacts of our product. Christian was not available to make a recording, so I will be reading his slide in his place. I was in charge of creating and updating the mind map. Due to my background in many of the more involved subjects that were to be included, it has since evolved to include our current design choices, such as a specific MCU, the use of a track for switching, and the specific converter to supply DC power. I was also in charge of researching which wireless technology we wanted to incorporate in the system. I started with a wide variety of options, narrowed it down to Wi-Fi, 6LoWPAN, Zigbee, and Wi-Fi mesh, and ultimately settled on Wi-Fi due to client demands, but also because it was a completely viable option that didn't compromise the project's feasibility. Lastly, I was in charge of providing the team any and all information related to the MCU, such as how the built-in communications function, modes of operation, power consumption, and a variety of other topics. This extends to the PCB as a whole, where I was often able to provide some insight into component choice.
My most significant accomplishment so far has been taking on the role of system engineer and helping to coordinate the Level 2 block diagrams with the Level 1 block diagram, ensuring that all of the interblock communications are consistent. I also took on the same role for Levels 1 and 2 use case diagrams. This task was extremely important as it will make the system integration possible in the future. I also created our initial system prototype, which was a cardboard model of what our finished product might look like. This prototype was very useful in helping us think about the relative sizes of each of the blocks. Later on, we were able to examine an existing similar device to get an even better sense of how these proportions should end up looking. Finally, I was in charge of creating and updating the stakeholder feature model. Throughout the semester, our user interviews yielded more information about what would be important to our various stakeholders, and our priorities had to undergo several revisions. Keeping track of which parties had a vested interest in which features became very important for us to refine the scope of our project.
Since forming this team in September, our team has grown to understand some of the professionalism and commitment required for being successful. Early on, we established group norms to promote team cohesion and to keep each other accountable for contributing. As the project developed and we became more invested, it became almost natural to follow these norms to the point where members are communicative, punctual, and engaged for all meetings. We also learned how to use our time more effectively during these meetings, coming prepared with assigned work, being concise in catching up team members, and discussing both long-term and short-term goals. Amongst the challenges facing the team that we are working on is improving communication and our relationship with our client. Throughout the semester, communication has been spotty with Ben, and we have been dependent on him for a lot of information. In terms of technical knowledge, we still have to put in a lot of time exploring and experimenting with Wi-Fi, as well as configuring our devices to a network. As well, we need to solidify what the impacts of our projects will be on a large scale, such as identifying outlets and mitigating heat effects. Lastly, we hope to be flexible so that if we ever need to pivot, we will be able to maintain focus and still provide value with our end product. Lastly, these are just a few highlights of the many things we have learned this semester. The first is that communication is key, whether it is with the client, professors, each other, or those from whom we are gathering information. If communication is lacking, there's less unity amongst the team, and this creates issues and failures. In terms of the design process, we learned that the beginning of design is about keeping all options open and brainstorming as many ideas as possible. Lastly, a device is just a small part of a larger picture. Our project is going to impact and be impacted by its surroundings, and this was something that we have learned as an important part of designing a real-world device. This semester has been incredibly helpful in setting up our development in the spring. We have learned a lot about the design process and have grown as a team from a technical and personal standpoint. Thank you for listening to our presentation, and we are open to taking any questions that you may have.